Tell me when you hit it.
Hit it.
Okay guys, today we will look at note card 74. And this is the first of several note cards that we will do. In fact, it's our last little unit of the year that covers volume. And we will look at a couple different ways to find volume. And the first one we will look at is called the DISC method for volume. What is the DISC method for volume? Well, first of all, let's just take a look at what we're talking about here, okay? Let me just make up some little region here that maybe we would have found the area under this graph. Maybe it's 1/4 of a circle or whatever. Now, notice that this graph, the shaded region, is flush up against the x-axis all the way from here to here. It's actually also flush up against the y-axis as well. Imagine if you took this and you rotated it 360 degrees, and it was some magic machine that was creating a solid. So we just went whoosh. Think about the solid that would be created, okay? We would have a circular end here. Does that make sense? Circular end. So we would be creating some solid figure if we revolved this around the x-axis. Now, whenever you do a revolution like that, you're going to have a circular part. So that's why you see pi r squared in the integrand for both of these formulas, because we know that pi r squared finds the area of a circle, and we would need the area of the base as part of the volume. So it makes sense that pi r squared is in these volume formulas. Okay, I could also do this and go around this way and create a different solid. That would be rotating around a vertical axis. If that's the case, we would be using dy instead of dx. Just like on area, we had area with respect to x, area with respect to y. So you can do the same thing with volume. If you were rotating about the x-axis, or about any horizontal axis, that would be with respect to x, dx. If you are rotating around a vertical axis, the y-axis or any other vertical line, then we would be integrating with respect to y. Both formulas are the same. One of them gets a dx, one of them gets a dy. One of them gets x limits, one of them gets y limits. Now, what do we call the DISC method? In the next lesson, we'll distinguish between DISC method and washer method, and we will do that when I come back. But the DISC method is used whenever your region is flush up against your rotation line all the way from the beginning of the integral to the end of the integral, from the lower limit to the upper limit, in other words. Okay? So the DISC method would be used here because we are flush up against. Okay? Just to give you an idea of when we, it's like, well, when would it look like something else? Okay, so let's say that we had, I don't know, just some region. How about we had a region that looked like maybe, let's see. How about this region right here? Looks like a little fish or something. If I rotated that, well, that's not flush up against the x-axis, is it? So we would need a different method, and that'll be coming down the road. So all we're doing right now is what happens when our shaded region is flush up against the rotation line from the lower limit to the upper limit. That's what's happening today. Okay, so DISC method for volume. We hopefully have an understanding of where these two formulas are coming from and how we know whether we're going to use dx or dy. And we know when we would be doing DISC method in the first place. Okay? So what are our steps for the DISC method? We're going to draw the region, just like we would do with area. We're going to find the limits, just like we would do for area. Then we're going to find the radius to set up an integral, and we're going to integrate and evaluate. So let's jump into this and look at number one straight off of an old test. Right? All right. The region enclosed by the x-axis, the line x equals 3, and the curve y equals the square root of x is rotated about the x-axis. What is the volume of the solid generated? And we're going to do this without a calculator. Okay, so we want to draw a picture first. So let's draw our x and y axis. Whoops. Move here a little bit. And let's put in our functions. First of all, I have a vertical line x equals 3. Whoops. We'll say that went through 3 there. So there's x equals 3. And I have y equals the square root of x. Okay, well, we know the square root of x. Let's see, it goes through the point 1, 1. And obviously it would intersect this at some decimal. But that's okay, because all I care about, I drew too much, I didn't need that. All I care about is this region here. The region enclosed by the, what's the boundaries here? Region enclosed by the x-axis, the line x equals 3, and the curve y equals square root of x. So it's this region here, isn't it? We're going to rotate that about the x-axis. So we're going to go whoosh. And you might notice that we are flush up against, the shaded region is flush up against the x-axis, all the way from the lower limit to the upper limit. So disk method will apply, and we will want to use this formula for disk method because this will be with respect to x, right? All right, so we've drawn our region, and now we need to find our limits, and we know our limits. This will be from 0 to 3, won't it? So far, so good. Okay, so let's start with our integral. Volume equals the integral from 0 to 3 of pi r squared. Let's hold off for a second. We're going to find that radius, and we know this is dx. So step 3 was find the radius and set up the integral. So I went ahead and set up the integral ahead of time, but now we need to find the radius, don't we? So let's think about the radius of this guy. Would you guys agree that the radius here would be linked to the function value of the square root of x at that place? Here the radius is longer, isn't it? It's still linked to whatever the function value is of the square root of x. So the radius is the function values of the square root of x. So the square root of x is what goes in for r, because it is dictating what our radius is. Okay? Okay, so now we have drawn a region, found the limits, found the radius to set up the integral. Now we're going to integrate and evaluate. I want to simplify this first. Pi is a constant multiple. In fact, from now on, guys, I would never, this is the last time you'll see me write pi on this side. I will always take pi out at the beginning of this because it's a constant multiple, so you might as well just move it out ahead of time. So I have pi times the integral from 0 to 3 of the square root of x squared. That simplifies to x dx. And now we're ready to bump up and divide. So I have pi times, bump up and divide, that's going to be x squared over 2. And we're going to evaluate from 0 to 3. So I have, let's just keep the pi out as a constant multiple. I have 3 squared over 2 minus 0 squared over 2. Antiderivative at, oh, sorry guys. There we go. Let me catch up since I had that off the screen. So I've got pi I took out as a constant multiple there, and then I had antiderivative at the upper limit minus antiderivative at the lower limit. So I've got 9 over 2 here. This is just a big old 0. So I have pi times 9 over 2. The pi can go with the numerator, of course, and I have a final answer of 9 pi over 2. That would be the volume of the solid that would be generated if we went and rotated that around the x-axis. Okay? Hopefully my sound effects will show up on the video. Alright, so there's number 1. Let me zoom out a little bit there so we can see the whole problem. Okay, number 2, we're going to do both with and without a calculator. So we'll do without the calculator first. Find the volume of the solid generated by revolving x equals the square root of 1 plus y with y equals 3 and x equals 0. And we are rotating or revolving about the y-axis. With and without a calculator. So let's do the without first. All right, first of all, a couple of key things. Y-axis. That means we're using this guy now. That means I need dy. That means I need y limits. Okay? All right, so let's graph what's going on here. Let's just graph over here where we've been graphing. Okay. All right, y equals 3 is, of course, a horizontal line. Right? X equals the square root of 1 plus y. Okay, so why don't we solve this for y so we can figure out what the heck the graph looks like, okay? All right, so if I solve this for y, let me tell you what, let me move over here and solve this for y. Let me just rewrite the problem first, the equation. I'm going to need to square both sides, aren't I? Square, square. So I have x squared equals 1 plus y. We get to break that out of the radical. Minus 1 to both sides. And I got y equals x squared minus 1. So it looks like I have the quadratic parent function shifted 1 unit down. However, I'm only going to graph the right side of the parabola. Okay, because look what's going on here. The volume of the solid generated by revolving this function with y equals 3 and x equals 0. Okay? So we don't need to graph this side because we're only using the shaded region on this side. Okay? So we've got this going on right here. And here is our region. The region bounded by the line y equals 3, the line x equals 0, and the graph itself of x equals square root of 1 plus y. The other dead giveaway that you only needed the right edge was, look at the original problem. When they solved it, if you solved this for x, you would actually get x equals positive or negative the square root of 1 plus y. They were only using the positive part, otherwise they would have needed a little plus minus sign in front of it. So that was the other way you knew it was only the positive side of the function there. Alright, so there we go. There is our graph, and that's what's going to be rotated about the y-axis, like that, all the way around. So we are ready for our integral now. V equals pi. I'm going to take out pi as a constant multiple. Remember, I want y limits. So the y limits are negative 1, 2, 3. Negative 1, 2, 3.
Coach, battery's about to die.
How much is left?
5 minutes.
5 minutes? Okay, we'll get through real quick. Okay, volume equals pi times the integral from negative 1 to 3. And the radius is the actual function. So the square root of 1 plus y squared dy. Alright, so here we go. Let's speed this up so the battery does not run out. Square root of 1 plus y squared is just 1 plus y dy. And now we're going to bump up and divide. So I have antiderivative of 1 with respect to y is y
3
plus
minutes.
Y squared over 2. And we're going to evaluate from negative 1 to 3. And I'm going to keep pi out as a constant multiple and just perform the first fundamental theorem here on what's left. So antiderivative at the upper limit minus antiderivative at the lower limit.
2 minutes.
Okay. Okay, 3 squared is 9. That's 9 over 2. And I have pi times 3 plus 9 over 2.
1 minute.
Oh my goodness. Alright, plus 1.
I can charge
and
it.
this is minus 1/2. Is it out?
No, I can charge it right quick.
Okay, so here's what we're going to do, guys. We're going to take a timeout right here.